All right. I wanted to comment a little bit on the course description questions um, because we've turned that in now, and I've put a grade in the grade book. So the first thing you were supposed to do was you were supposed to look at these four goals on here, and basically I just wanted you to just write them down. And because these are ones that really stand out to me, students should be able to work with functions. Think about how we've been talking about functions here a lot already. Represented in a variety of ways, graphical, numerical, verbal. They should understand the connections amongst these representations. Students should be able to communicate mathematics and explain solutions to problems both verbally and in written sentences. One of the things you will find, not so much maybe on this first quiz, a little bit maybe, is that a lot of the questions in the book ask you to explain or justify your answer or whatever. As you read in the course description, it talks about how you're supposed to answer questions on the AP test, and we will pattern ourselves after that all year long. When it comes to the AP test, if you choose to take it, you will be well prepared to do that because you will just be in a habit of those types of questions, those style of questions, and how to answer those as we go through the year. Students should be able to use technology to help solve problems, to experiment, to interpret results, and support conclusions. And we know about the technology we're using. And then this is an important one, I think, as well. Students should develop an appreciation of calculus and Students should develop an appreciation of calculus as a coherent body of knowledge and as a human accomplishment. My high school math teacher, who was a great guy and a great teacher, and one of the reasons I became a math teacher, but he would always talk about the beauty of mathematics, how beautiful it was. And of course, we would behind his back, but we would, and he would, but he was so into it and how beautiful it was. And to be honest, I mean, there's a certain amount of that that is true. I mean, it is true. And so hopefully part of this, why did you sign up for calculus? You could have taken AP Stats. Many of your classmates did, right? Maybe that fits better with what they're going to go into. That's fine. So maybe you need it for engineering or whatever. You're going to be business, you have to take a calculus class, whatever. So maybe that's why you took it. Could be a lot of reasons you took it. But hopefully, not only do you get that out of it, but you get some appreciation for this kind of, like I say, human accomplishment of what is calculus and what makes up calculus. Prerequisites. So all this stuff in here, and so you went through there, and I asked you to name some of the things. Piecewise function was a big one that a lot of people named. Some of you talked about the trig values or the trig functions. Talked about that. Today, here it says students must understand the language of functions. That's supposed to be a prerequisite. We're reviewing that right now. Our first quiz is going to be a lot about that, domain and range. Today, we're going to talk about odd and even functions. We're going to talk about periodic functions. We're going to talk about symmetry, zeros, intercepts, right? That language of functions, that's going to be a big part of what we do in today's homework because it's about graphs and so forth. All right? You should be familiar with different types of functions. The graphs of functions, polynomial, rational, exponential, that's tomorrow. Tomorrow, section 3, we're going to talk about polynomial functions. We've already talked about exponential log. We'll talk about them a little more. We'll talk some trig tomorrow. Inverse trig will be in there. I don't know if we'll get to much of that tomorrow. We've already talked about piecewise. Okay, so we're hitting a lot of this stuff right in here that's in the prerequisite area here. Okay, then what you have is a whole big, these are all the things we're going to learn. Okay, these are all the topics, things we're going to do, and there's a few even outside of this that we're going to talk about. Okay, all right. Then we get into the AP exam. So you had to answer a question about the AP exam. It's 3 hours and 15 minutes. There are two parts. One part is 45 or 105 minutes. You have 45 questions. That's the multiple choice. Okay, now that's broke up into two parts. The first part of the multiple choice is 28 questions in 55 minutes. That's roughly 2 minutes per question. Okay, it's very tough. That's probably the hardest section of the test, I think, is the multiple choice without a calculator. Okay, the multiple choice without a calculator. About 2 minutes per question. Not everybody, you can't get rushed having to get through that. Okay, when we do our final, when we do our midterm, we'll do something very similar to that. Our midterm is going to be over 2 days, and there'll be what I'm going to do is a calculator day and a no calculator day. And there'll be a mixture of multiple choice and free response. It will not be as long as the final. Okay, but that's going to be two days. The final is going to be 4 days. Okay, now we will again. So it's like 4 quizzes. Right? It'll count like 4 quizzes. Now it'll be spread out. We'll do a day. We'll have probably a review in between, or go over it kind of thing, then another one. So it'll be spread over about 8 days probably. And it's towards the end of the year, and it'll lead up right up to the AP test. Right? We'll have about a week or so left of class after the AP test. I think the AP test is on Wednesday, and your last day is on the next week. Okay, so we'll finish that up there, and then we got a paper and some group problems that we will be working on that last week. Okay, that's a long ways away. But those 4 parts mirror these 4 parts. So we'll have one part that is the multiple choice, 28 questions, you'll get 55 minutes. And you don't get to use a calculator. Then the next part is 17 questions, you have 50 minutes. So that's about 3 minutes per question. So it's quite a bit fewer, but it's almost the same amount of time. I think they figured that you need, if you're using your calculator, it's taking longer because you're having to type stuff in. Okay. Now, just because, notice it says, contains some questions for which the calculator is required. Not all the questions would you even use a calculator. Just because it's the calculator section doesn't mean you're going to use the calculator necessarily. All right, then there's the free response section, which is where you answer questions just like you normally do on a math test, where you work it out, show your work and everything. Okay, that is half of your AP test grade. Now there are 45 questions, multiple choice. That's half of your grade. The other half comes from these 6 questions. 6 free response questions that are broke up into parts, A, B, C, and D, or depending on the question. Some have 2, 3 parts, some have maybe 4 parts. The first part is 2 questions. You get 30 minutes, so that's 15 minutes per question. But you get 30 minutes for those 2 questions. And some of those you may need a graphing calculator. Some questions or parts of questions you'll need a calculator. The other part is 4 questions. You get 60 minutes. Again, 15 minutes per question, basically. And you cannot use a calculator on that. Okay? Now, it says during the second part, you can go back to part A, but you can't get your calculator back out. Now, we will do something similar to that, but I will let you get your calculator back out. So when we start on our test, we will do the calculator part first. When we do a quiz where we have both parts, we'll do our calculator part first. Then you can hand that in, put your calculator away, and then pick up the no calculator part. Or if you want to, you can keep the calculator part, put it on the floor, put your calculator away, do the no calculator part, hand in the no calculator part. Then I will let you go back to the calculator part and get your calculator back out if you want. On the actual AP test, if you want to go back to the calculator part, you can, but you can't get your calculator back out. So a small difference there. But anyway, you'll see how that all works when we get to that point. Okay, and then finally, the last questions were, what can you use your calculator for? There were 4 things. Okay, you can use, now when we say what can you use your calculator for, there are 4 things you can use your calculator for without any supporting work. You can do a graph. So if they want a sketch of a graph, you can graph it on your thing and then just put it on your paper. You don't have to show a table of values, you don't have to pop points, anything like that. You can use your calculator to do a graph. You can find zeros of a function, which basically means to solve an equation. So if we do that solve thing, like I showed you on the calculator, solve the equation, you can use your calculator to do that. You don't have to show the steps and everything. You do, however, have to have the equation written on your paper, which we'll get to in a minute. It can numerically calculate the derivative of a function, which we're going to learn about, and it can numerically calculate the definite interval, which is something we've talked about as well. Other than that, everything has to be shown on your paper. So, back to this, the true-false questions that you turned in. The first one said something about, is a calculator answer sufficient? And the answer is, or it's never sufficient. The answer to that is true. Now, I suppose technically some of you had false, and when they say never, I suppose there's some leeway, but I didn't really count off for that. But right here, for solutions obtained using a calculator capability other than one of the 4 listed above, students must show the steps necessary to produce the results. A calculator result alone is not sufficient. Now, it does say 4 solutions obtained, but basically they call that a bald answer on the AP test. You have an answer, nothing around it, which many of you had for number 19, by the way. Right? You have an answer for number 19 from the back of the book without anything else around it. That's usually not good. Okay, that's usually not good. Especially if you use your calculator. Okay? Now, it says if you obtain a result using one of those 4 capabilities listed above, you are required to write the setup that leads to that solution. These setups include the equation being solved, the derivative being evaluated, or the definite interval. So if a problem involves finding the area of the region and the area is used using a definite interval, you will have to show that setup written in standard mathematical notation. That was another question on there. Can you use calculator syntax? No. Right? You need to have your normal calculator result. And then here's the part where it talks about the 3 decimal places. This is one last thing, and then we'll move on to homework. Students should be cautioned against rounding values in intermediate steps before the final calculation is made. Okay? So if you have a calculation and another calculation, then you put those 2 calculations together to get your final answer, you don't want to round. I usually say leave 5 or 6 decimal places in your calculations as you go through the problem so that the final answer will be accurate in 3. Okay? So that's kind of important as well. All right, let's move on. Number 12 I want to look at. Oops. Number 12 I want to look at, and I want to look at number 19. Are there any others that we need to look at? We can talk about 28. Is 28 the absolute value one? Or is that 22? That was 22. What about that? Do we need that one? 28. What was 28? Oh, graphing. Well, let's start with these, and then we'll see if anybody wants anything else. So this was 12, right? The reason I want to do 12 is I said that this would for sure be on the quiz on Tuesday. So we talked, if you were gone, there is a video, by the way, if you were gone. Was somebody gone? Somebody gone? Okay, so there is a video up about yesterday. But quiz on Tuesday, starting with the things we were doing yesterday and moving forward is pretty much what the quiz is based on. It's a lot about language of functions and those kind of things. And one of the things we want to be able to do is do a piecewise. Okay, so let's just run through this. Since I told you this was going to be on here, I want to give you one more practice at this. We will probably not do another one. Now, I will say this. I don't know, somebody in the last class asked about it, and their only question was this thing right here. This is a typo. In your book, was it off a little bit? I apologize for that. I should have said something yesterday. This is supposed to be like that. Now, if you went ahead and worked it with approximations for what that was right there, then good for you. That's fine. At least if you did the rest of it right, you got the main idea. On the quiz, I'll be very specific about that. But these are the points. This is where it goes through. Okay? I think just when they printed the book, that printing got off. And it got off on my transparency here, and it was not supposed to. Okay? So what we have is a line. Now, what would be the equation of this first line right here? Y equals -2. So when we come down here, we already have the y equals for our piecewise function. So it's y equals -2. And then that goes from -5 to -3, just like that. So that piece goes from there to there. That's how we do a piecewise function. Okay? Now, let's do this other line over here. We had, and then we'll do the circle. So we had y equals m times x minus the x point plus the y point. All right, so what's that slope? -2. So that's going to be -2. I'll just write it down here. -2. Let's do this point right here, which is what, 2, 2. So it'd be x minus 2 plus 2. And then that goes from 2 to 5, like so. So the lines are pretty easy. All right, now, the circle. So yesterday, let's do this in red. So the circle, we said the x minus h, this is an equation you're just going to have to know. X minus h squared, y minus k squared equals r squared. And we just got to know that. Looks like the center is at 0, -2. So this would be x minus 0 squared, y plus 2 squared equals, what's the radius? 3, so 9. Now we said we got to solve that for y. So this would just be plain old x squared here. we're going to subtract that over. So we would have, let me do it over here. So we would have y plus 2 squared equals 9 minus x squared. Now, we can square root both sides of this now. And I talked with a couple people that were mentioning that, well, you know, we can't distribute that squared through there. We can't do that. But we can, at this point, we have the quantity squared alone on one side. We can square root both sides. Now, that's when we have to do the plus or minus. We get plus or minus square root of 9 minus x squared. Okay? Now, let me make a little side note on this because this is one of my pet peeves. That's probably not the right word, but it's just one of those things that people misunderstand, and I want to make sure we get this. If I ask you for the square root of 16, I just say, what's the square root of 16? What do you say? Now, I'll bet if I had asked you a month ago, what's the square root of 16? If I had walked down the hall and I said, what's the square root of 16? You'd all said 4. You wouldn't even have thought of plus or minus. But now when you talk about plus or minus, you think about it. Well, you'd have been right a month ago. It's 4. It's not plus or minus, right? The square root of 16 is 4. But if I ask you to solve this equation, x squared equals 16, what's the answer? X equals plus or minus 4. Those are two different questions. One question is saying, what is the solution to this? What are the x values that will make this true? Well, 4 and negative 4 will make this true for x. But the square root of 16 is just 4. If I want the negative version of that, then it'd be negative square root of 16. That's negative 4. Okay? So those are two different questions. And that's important to understand it. So when I want to graph the function y equals square root of x, right, what it is the top half of a sideways laying parabola. We'll get into that more tomorrow. That's the graph of y equals square root of x. So you plug a 16 into that, you get out 4. Okay? You don't get out 4 and negative 4, then it wouldn't be a function. Right? Failed vertical line test, all that bit. All right, so anyway, those are two different ideas. So when we get back to this, okay, what we're doing is we're solving an equation. So when we do the square root of both sides, we have to put plus or minus. All right, and then we take away the 2, and so we get negative 2 plus or minus square root 9 minus x squared, or we can put it on the back end, whatever, doesn't matter. So that goes in here. So we got our y equals, and then negative 2 plus or minus square root 9 minus x squared. Oh, thank you. Thank you. Yes, you're right. Okay, back up. This is wrong. Plus or minus means what in this problem? Top, bottom half of the circle. Top, bottom half of the circle, right? Positive is the top half, negative is the bottom half. We have the top half. So we only want the positive one. That's right. So, thank you. Sometimes I like to do that on purpose just so you can. All right. So, got a plus in there. That's what we want. Don't put the minus in there. That would cost you a point on the quiz problem. All right? Negative 2 plus square root of 9 minus x squared. Now, some people might say, well, wait a minute. It's not the whole top half. It's only part of the top half. That's what this will take care of, right? So right now we're going to go comma, and then we'll say, okay, the circle starts at negative 3, but I don't want to include it because I already included it up here. So I'll go negative 3 all the way around to 2, and I don't include that either because it's got an open circle. Okay? So that'll take care of that. Now, would you ever have, so you might just have a quarter of the top half or just a part of the top half or whatever. That gets taken care of there. You still write the whole equation for the top half. Would you ever have part of the top half, part of the bottom? No, because then that wouldn't be a function. So you can't have a piecewise defined function if it's not a function. Right? So you won't ever have part of both. You won't have it. Okay, so there you go. You're going to have to be able to do that on our next quiz, and we probably will practice another one between now and then. So you'll have to come back and revisit that. And I'll remind you that. But all right, let's move on here. What else did we say? 19? Okay, let's take a look at 19. So 19, now this is probably not something you really need to worry about for the next quiz. But what this is about is creating a function. And this is a little bit of foreshadowing, kind of like we did earlier last week, where we look ahead to things we're going to be needing. Okay, and so that's kind of what this problem's about. creating a function. So we're talking about language of functions, being able to read what this says and everything. And so they tell us we have this function L, 2x plus 1. So I'm going to graph that. Let's make that a 1 and 2. I'll go every other one here. Now this is what I was looking for in your paper. I wanted to see if you at least graph the line 2x plus 1, and many of you did not even do that. Okay, I don't know how you could do this question. I don't know how you could come up with this trapezoid thing without a picture. I think you need to. Now, we're going to talk about graphs today. There's going to be a lot of problems. A lot of your homework problems today are going to be about points on graphs and stuff. I think you're going to need to draw those things. I think to be able to see them, I think it's really important. So, this would have a y-intercept of 1. We would go up 2 over 1, up 2 over 1. Oops. There we go. So we would be looking at this line right here. This would be the line L. Is 2x plus 1. All right. Now, it says we are going to have a function a of t. It said let a of t be the area of a trapezoid bounded by the x-axis, which is down here, the y-axis is up here, this line, so it's going to be bounded here, and the line x equals t. Now, some people had difficulty with that. What if I had told you the line at x equals 2? What's that? Vertical line at 2. X equals 3. Vertical line at 3. So, if we have x equals t, that is vertical line somewhere at some unknown place t. Now, it does later in the problem say t is going to be between 0 and 5. Okay? So we're going to have a vertical line somewhere between 0 and 5. Now, since my picture only goes to here, let me draw it in here somewhere. All right. So, anyway, we've got this blue line in here, or the black line. The blue line here is going to be x equals t. So I'll just draw it in here somewhere. That is t. All right? Now, this could move. Imagine that dashed line moving, sliding back and forth. Now, do you see the trapezoid? Isn't that a trapezoid right there? Two parallel bases. Now, we're used to seeing, I understand what you're thinking. You're used to seeing a trapezoid that looks like this, right? Oh, no, you are not used to seeing a trapezoid that looks like that. Okay, here we go. Okay, something like that, where you've got these two parallel bases, like so, and the height would be the distance between the parallel bases. But that's not the kind of trapezoids we will be seeing mostly in calculus. The type of trapezoids we're going to be seeing are very much like this trapezoid, very much like the trapezoid you saw this time. Anyway, we got this, parallel base, and where's the height on this? This is the height actually down here. So this would be B1, this would be B2, and this is the height. And you remember the area of a trapezoid is 1/2 the sum of the bases, which is basically saying average those two bases, and then times the height. So it's really a rectangle formula is what it is. Okay, but usually these are the kind of trapezoids we have. So kind of tipped up on their end, but it's still a trapezoid. All right. So there's all kinds of things in this problem that are tricky, and there are things you've never really seen before. You've never probably had a problem, anything like this, where it was asking you to create this thing. So I understand that it was tricky, okay? But the next time we see it, it better not be as tricky. And then as we see more and more of that, it should become quite simple, actually. All right, so we're trying to get that area. Okay, so we need 1/2. Now we need B1 plus B2. And then we went out here, we want the height, right? Times the height out here. Okay, so let's look at it. Now again, imagine this blue dotted line, imagine that just kind of moving around, sliding at different places. Because notice, t is the input of our function. So an area is the output. So what we're saying is we're creating a function here, so for various inputs, for various different right edges, we get different outputs. Okay, yeah, all right, that's the function. So what is B1 here? That's never going to change, is it? We slide that dotted line around, that is never going to change, that's a 1. Okay, what about B2? That's this height right here. What is that height right there? 2t plus 1. It's changing. That height, that y value, is going to be different depending where the blue line is. Well, how do we get the y value? Well, we just plug into there. So if this blue line's at 1, we plug a 1 in for x, and that would be the height. If the line's at 2, we put a 2 in for x, and that would be the height. But right now, the line is at t. So this y value is what you get when you plug a t in for x. So 2t plus 1. Another way to think about it is this. This point right here is the point t, 2t plus 1. Right? The x value is t. The y value is 2t plus 1. All right. So that B2 is 2t plus 1. Okay, and what's the height? We said that was this. That is t. All right? So the height is t. So we go ahead and we simplify this. Inside here we get 2t plus 2 times t. We distribute the 1/2, makes it t plus 1 times t. And then we distribute and we get t squared plus t. So you can see my, when I walk around and I look at your homework and I look at number 19, because that's typically what I do, is I have several of the homework questions in mind that I know required a little bit of something. And when I walk around, I'm looking on your paper for those particular questions, see what I see. And when I walked around for number 19 on a lot of papers, I would just see this. Well, how in the world would you ever gotten that? Right? I'm not saying it's bad to look it up and write it down so you have something down there. I get that. But, if you've got a bunch of those, that's not good, right? Because if you're just looking for the 2 points you need for your homework without understanding what's going on, well, quiz grades are going to more than make up for those 2 points you got in the homework, and it's not going to be pretty. So, ask, come in and see me, whatever. But this is for sure one we're going to look at. So there it is. And then the last question, part B, then said, graph this. Okay, well then just get on your calculator and graph that, except remember, you can't use t's, you got to use x's when you graph on your calculator. So then that's all they want you to do. Okay, so that's not a big deal. All right, any others? We mentioned a few others. I don't know if those are ones you see or not yet. 28. Okay, which one was that? The graphing one? All right. So that would be, all right, so that was a piecewise. Now, and by the way, somebody asked this. That was a good question in the other class. They asked if we had to do, it's gone. Well, we'll get to it here in a second. So on this piecewise one, they say that the first part of the graph is 0, and it says, what do they say? When x is less than or equal to -1. Now, they wrote it like that when they did their piecewise function, right? They've got their piecewise function like so. I would have written that as -∞ to -1 like that. I don't care which of those you use. So the question came up in the other class, can we use this, less than, and those kind of signs, or do we use this? I don't care, but it's just that we do intervals so much that these are way easier and shorter. And I think it's just a good habit to get into. Okay, it's like when we do domain and range. I think you ought to use those as your interval notation. Okay, but if you use the x with the less than or greater than, that's okay too. All right, so 0. So let's make this 1, 2 again. Let's go by 2. So this would be -1. So we're going to get 0 this way, right? Forever. So we're going to have that for the first piece. The second piece was what? 3x minus 2 from 1. Did it include them both? It didn't include either one. 1 to 1.5. Okay, now they wrote it in that less than notation, which is fine. But they were actually wanting that. All right, now what I typically do when I graph these is I graph the whole line. I don't try to just graph it from there to there. Now, it's up to you. It's probably just as easy. I mean, So whatever you'd rather do. One option would be to say, oh, 3x minus 2. Okay, that's going to be y-intercept down here. Go 1, 2, 3 up, 1 over. 1, 2, 3 up, 1 over. Connect it, right? And then just erase all of it except this part. So I think that's a pretty good way to do it. Now another way to do it is to just plot these endpoints. Since you know it's a line, you can just plot these endpoints. Okay? So especially on lines, that's a pretty good way to do it. So at 1, if I put in a 1 here, I get 1. So I know I'm going to have the point 1, 1. Now that's going to be an open circle because I'm not including it. And then plug a 1.5 in. That'd be 4.5 minus 2. That'd be 2.5. So 2, 1.5. No. Well, right. Yes. So it'd be 1.5, and the output would be 2.5, which is right there, right? And I know it's a line, so it's just going to be connected to there like that. Okay? So one way to do it is to just graph the line 3x minus 2, and then erase all of the parts you don't need. Or you can do that. Now, it gets a little trickier with this one because it's x squared. And that's supposed to go from, and it includes 1.5 and not 2. Okay, so it's like that. So it's a little trickier here because this is curved. So you can plug 1.5 in here, and you can plug 2 in and get those, and then just curve it a little bit because you know it's a parabola. But basically, x squared is this parabola here, which goes like this and goes like this. And so what we're looking for is just one little piece of it. We're looking for this little piece right in here, right? So it's curved. So to be a little bit exact, probably, plugging in these endpoints might be the way to do it. So if you do 1.5 squared, what is that? Oh, did I graph that right? Yeah, I did. Okay. So at 1.5, you square it, that's 2.25. So right here, we're going to be at 2.2. So we're going to be just below that. And then at 2, we get 4, which would be up here. Oh, whoops. And that's not included. Okay. Open circle. Okay. Open circle at 4. And so from here to here, it's coming from here, it's coming up, it kind of goes through 1, 1, it's going to hit here, and it's going to curve kind of around by that, something like that. Something like that. Okay? And it passes the vertical line test because this one's open, that one's closed. You wouldn't want both of those to be closed. That'd be bad because then that would fail the vertical line test. But, so there it is. There's your piecewise function. Okay. Anything else? 22, was that the one with absolute value? Yeah, I did want to comment on that. Now, absolute value, the function absolute value is what kind of graph? What's it look like? Let's go. Yeah, it's a V graph. It's a V graph. Now, if you think about this, though, isn't that a piecewise function? It's two pieces, right? It's a line and another one. And so part C actually should be, now that we've kind of talked about it, it should be like, oh yeah, that's what absolute value is. I mean, you think, what are those bars? Why are those bars here? It has to have a mathematical definition. This is the mathematical definition of what absolute value is. If you think about it, it says exactly what we say when we say it in words. So let's just do it. What's this piece? Well, it's a line. Y equals, what's the slope? -1. And this would actually be one of those that would be easier to do y equals mx plus b. Because the y-intercept is 0. Anytime I got a y-intercept 0 and I know the slope, I'm just going to do that. Because if you know the y-intercept real easily, then y equals mx plus b is real easy to do. Slope and y-intercept. So that's just -1x, which is just negative x. And then that goes from where to where? -∞ to 0. And we can include the 0, not include the 0. Usually we include the 0 on the other one with this. Okay, now what's this graph? That's just y equals x. So y equals x from 0 to infinity. And that's it. I mean, that's what absolute value is. Now, if you think about it, that's what we would say absolute value is. When you explain to a sixth grader what absolute value is, you say it makes it positive. It makes it positive. Well, isn't that what this is doing? This is saying when x is negative, do what? The opposite, right? The opposite, because that's really what that means is opposite. This is another thing that drives my algebra kids nuts. I hate to always throw those guys under the bus, but still. Is that a negative or a positive number? It depends, right? It depends. But how do we always read that? Negative x. And I'm just as lazy and guilty as you guys. We should read that opposite of x. That's really what that means, the opposite of x. Because negative x might be a 5. And x might be negative 5. And that just blows them. They just can't figure out that negative x would be 5 and x would be negative 5. How can that happen? Okay? All right. But, and it would have probably done that to you when you were that age. You're a lot younger, also. So, but that's what this says. This says when x is negative, absolute value is the opposite of that. And when x is positive, it's just that number, right? That's what it means. Make it positive. Make it positive. Okay. Ryan told me I was being too mean to my algebra and B students, but still, sometimes it's just crazy. All right. So what else on 22? Domain. What's the domain? All reals. Now you can write out all reals if you want. That's perfectly acceptable. Or negative infinity to infinity. That's another good way to write algebra. I don't care. Either way is fine. Domain is all the possible x values that you get a y value at. Okay, what about range? 0 inclusive, and then infinity, right? Again, 0 starts down here, and all the y values go up from there. Okay, good. All right. I would comment about number 30 then real quick. Wasn't 30 the one that was square root of 4 minus x squared? And did they just want domain? Just ask for domain on that. So what I would do is this. I would think, actually on this one it helps me just think of a number line. I don't care what the graph looks like because I don't have to do range. But when you're thinking domain, you're thinking what are the possible x values I can plug in? If you have a graph, it's easy, like the last one. We had a graph. If you don't have a graph, it's not quite as easy. So you got to think to yourself, what are the possible x values that will give me out a y value? Well, to start that process, you probably ask yourself, what won't give me an output here? A negative inside, right? So what would cause this to be negative? Well, 4 minus 5 or 6 or 7, something bigger than 4. Well, what will make this bigger than 4? So yeah, if you get out here, that's going to be bad. But also, if you get out here, that's going to be bad. Negative 3 squared is 9. 4 minus 9 makes a negative. So it turns out you want everything that's in between there. Now, is 2 and negative 2 okay? So you would include those. So negative 2 to 2 is your domain. Everything in between negative 2 and 2. So that's the thought process when you have the equation like that and you're looking at domain. The biggies are negatives in the square root and 0 in the bottom of a fraction. Those are the two big ones for domain, okay, where you have to think about it. Then the other ones are ones you just have to know the function. For example, this function, this is one we're going to talk more about tomorrow. Anybody know the domain of that? What are the allowable things you can plug in and do the log of? Can you do the log of a negative 2? Remember, this is base E. Can you take 2.7 and raise it to something and get a negative answer? There's no way, right? Because if you take 2.7 and raise it to a negative, what's that do? Just flips it, right? And you raise it to a positive, that's going to be positive. There's no way you can, matter of fact, there's no way you can do 8, so there's no way you can take any base, raise it to something, and get a negative, right? So the natural log function domain is this, right? And you can't ever get 0, right? Is there anything you could take a base and raise it to something and get 0? No, because if you raise a 0 power, you get 1, right? So the natural log function is this. Well, that's just something you have to know. You just have to know that the log function has that domain, that you can only plug positives into, right? And we're going to learn more about that and talk more about that as we go into tomorrow's section. All right. Let's take a look in your book then. You're probably already there, but let's take a look at page 12. And let's just run through a couple things on the section 2. Most of this is review stuff. A couple things I want to talk specifically about. Okay, on page 2, they've got a picture of a graph. That's our main emphasis here is graphs. Okay, so they have a picture of a graph here, top of page 12, with just your function notation. We've been already doing this, so none of this is new. We want to get used to this idea, f of a. When we see f of a, we think output, y value. F of 2, f of 1, that means the output, the y value. Okay, so we want to be able to read a graph for sure. Okay, if we look over on page 13, let's see, is there anything on page 13? Oh, they talk about intercepts, x and y intercepts. We all need to know what that's all about, x and y intercepts. Talks about a function. Well, let's turn to the next page. Page 14. Now, there's a whole bunch of stuff in boldface type, and we want to know all about this stuff. Okay, roots. Where's a root of a function? What's that mean? A root. Where it crosses 0, which means crosses which axis? The x-axis. So if you have a graph like this, these would be roots, right? That's where f of x is 0. So if I tell you f of 2 is 0, I'm telling you 2 is a root. Now, by the way, if I tell you f of 2 is 0, what I just told you is the point 0, right? Remember I said that to you earlier? Ordered pairs mostly this way. Right? So if I tell you f of 2 is 0, first thing I would do is draw myself a little picture, plot a point, 2, 0. Right? There's going to be some of your homework problems where that's going to be what you're going to want to do. But roots, that's something we are interested in a lot this year. Okay? If you think back to that balloon graph we were talking about yesterday, the balloon going up and down, on the velocity graph, this is when the balloon changed direction. Right? Because that's when its velocity was 0. So the roots often hold important information for us. Okay, so roots. The next section talks about local max and min. Let's do this. Let's say we got a graph that looks like this, kind of a sine, cosine kind of thing. This point and this point right here are called local maximum points. Local maximum. Now it looks like the second one is higher than the first one, but that doesn't matter. They're both local maximum points. Local means in that small little area, they're the highest point. So think of it like a peak on a graph. Now also, if I had a V graph, kind of turned upside down, that's also a local maximum point, right? So we're going to have curves. And then later we'll talk about the difference between one where it's curving and one where it's a sharp point like the V graph. Because there is a difference there. But for now, we just understand those are called local maximums. And likewise down here, here, and here, we have what's called a local minimum. That is going to be a term we'll use a lot. Now another term that books used to use more is relative max and relative min. And that means the same thing. Okay? Local max, local min, or relative max, relative min is kind of the same thing. And again, if we had a V graph like so, that point would be a local minimum as well. Okay? So just some terminology that you need to be aware of. It's not anything real hard. Increasing, decreasing, when the graph goes up, when the graph goes down. That's pretty self-explanatory. Okay, the next section, let's go back to another similar picture again. And this time, we're going to introduce some new terminology. Right here, in this section, this graph is what we call concave down. And same thing over here. This graph is what we call concave down. Okay? The curvature of the graph. The curvature of the graph. And in between here this is called obviously concave up. Now don't confuse that with the word convex. I don't even know what that means. I know in some class you probably use convex versus concave. We just use the terms concave up or concave down. Okay? All right, and these 2 points, what's happening at these 2 points here? It's switching between concave up and concave down, and that is called an inflection point. So there's always got to be a point where it switches concavity from one to the other, and that point is called the inflection point. And something special is going on at that point that we want to talk about as well. Well, you can probably just tell. Just think steepness. In this region right here, where's the steepest point? That point, right? It's getting steeper, getting steeper, getting steeper, and then right here it starts getting less steep. That point's the steepest point in that little area. So that may have ramifications like we talked about rates and things like that. Okay, so that's it on that page. Well, I guess down at the bottom of page 14, I guess I should mention this. They give you this graph. This kind of fitting with the Ebola virus, right? This is supposed to be a graph of some epidemic, right? And S is the function is susceptible, those people that could still catch it. R is those that have recovered, and I is those that are infected. Now, what I'm saying to you is if I may give you a problem with a graph in context, tell you about what it stands for, and then ask you questions about it. So, and I might ask it in function notation. So, for example, in this one, you know, I might ask, okay, on this graph, what is S of 5? That's an S. What is S of 5? 37,000. Or I might ask this. I might just give you this and say, what does that mean? After 5 days, are still susceptible or still have not caught it or whatever the description is. So you write it out in words what that particular mathematical thing would mean. Okay? So, I mean, that shouldn't be that difficult either. It depends. It depends on the wording of the problem and what it stands for and how to read the graph and so forth. But I want you to be able to read off of a graph, interpret what it's saying. Okay, top of page 15. Remember we talked yesterday about a table of values. You don't know what's in between those points. It doesn't have any points. So if you look at the graph on the bottom left, it could be just a series of dots. Now, it could be, though, that I give you a table of values and some context to the problem. So in other words, I might say, here's a table of speeds. I check my speed every 5 minutes. You know, so 5, 10, 15, 20, 25, 30, and I give you those speeds. Now, you know there were speeds in between. So you can plot those points and you could guess kind of what's happening in between there, make some assumptions about what's happening. And that's what those other graphs are doing. They're kind of making some assumptions of what's happening. So you know there would be other points, you just don't know what they are. Okay? But without context, we wouldn't, right? We would just, the function would be just those points, like we were calling it undefined yesterday. All right. Last thing here, well, not last thing, I mean, but the next thing on page 16, turn to page 16, 17, and then on to page 18. They talk about that shifting and stretching and compressing and all of that stuff that we had talked about on our algebra review page. So I don't want to spend a great deal of time going through that today. But I will show you, I will tell you that that document, if you want to open up those documents that I gave you, if you go into your menu, or your docs, excuse me, or go to the home screen, it's probably fastest. Go to the docs, the home screen, go to My Documents, and then pull up the one that says Translating. Okay, is it taking a while? Yeah. Okay. Well, while you're waiting for it to stop spinning, I'll show you up here what's going on if I can get to it. Okay. Here it is. Oh shoot. All right. So, for some reason it works on this one and not on that. All right. So what you can do when you get to this page right here is you can click and you can drag this thing around. Now, an easy way to click. You see, I got the little hand there. The open hand, if you hit control and click the middle of your trackpad, it'll close that. If you click and hold, I think it will as well. Maybe, maybe not. I think control click is probably the way to go. So you hit control and then click down there. Okay, why can't I get the hand back? There it comes. Oh, come on. Okay, there we go. I don't know why I don't have the hand on there. But anyway, this is just showing that if I shift to the right, now yours may work a little slower than mine on the computer, but a shift to the right is a number on the inside of the parentheses, inside the function. The shift to the left is +1, +2, like we know. If we shift it up, right, that's a +3 on the outside of the function. If you shift it down, so it just allows you to move this around and kind of see what it does. And so, you know, if you need a little extra looking at those, you can look at that page. The next page has a whole variety of functions we can look at. So if I go to the next page here, I got the V graph. Now in this one, I do it a little different. I come grab this slider over here, and I grab this slider and I move it up and down. So I go, come on. So I move the K up to a 1, to a 2, and we notice on the outside it does that. I move it down. Okay, it does that. Now I can also click up here where it's got this little up arrow here. It says click, and it'll run through a variety of other functions. So here's a piecewise function. So we can just watch what a piecewise function looks like when we move it, when we slide it up, and slide it up and slide it down. It's working really well. Okay, and we can see how it just takes those points and just moves them and so forth. Okay, and that's that document. And so if I want to, I'm going to go to the other document now, and it may ask you if you want to save. So if you want to go back to your home screen, open the other one, it'll ask you to save. I usually say no, because it just, you know, that'll keep it back the way it was originally. Okay, and that may take a little while to open yours up as well. But on this one, this one talks about dilating. That's another term for stretch and compress and so forth. But now this one's just going to show if you multiply on the outside by a number, that's going to stretch it vertically. So if I take this, so what you do on this first one, you just grab this point. So if I go up to a 2 or a 3, you can see we got a vertical stretch. Okay? And we talked about that. You can kind of see how that looks. And then if you drag it a little lower, but not all the way to the x-axis, we got a vertical shrink or a compression. So that's like a 1/3. And you can see how that affects it. Then if you drag it below the x-axis, then we talked about how you get that reflection. So you have a negative on the outside, you got a vertical movement here. So think about what we got. We got horizontal shifts, we got vertical shifts, we got vertical stretch, we got vertical compression. When it's on the outside, it affects it vertically. And then if you got a negative on the outside, it's a vertical flip or reflection. Now what this document doesn't show then is the horizontal movement. So let's talk about that real quick. So if I take a function, if I have a 2 on the inside, with the x, what is that? Horizontal what? With the 2, is it a stretch or a shrink? Remember, the numbers on the inside work the opposite of what you would think. So this is a shrink or a compression. A 2 multiplied on the inside is actually a shrink. If you would have a 1/2 multiplied on the inside, then that is your stretch. Okay? So a 1/2 would actually stretch it horizontally by a factor of 2. So that means wherever your point is, it would now be twice as far from the y-axis. Either direction. Okay? Either direction. And then if you put a negative on the inside, horizontal flip. Put a negative on the inside. So the idea is any action that's happening on the inside is going to affect it horizontally on the x, and any action that's happening on the outside of the function is going to be a vertical movement or stretch or reflection or whatever. So You're going to have some questions today on the homework about doing that, about drawing, sketching some graphs and stretching them and shrinking them and compressing them and all that good stuff like you did on that packet. So you're going to have a problem there where you're going to have a bunch of different graphs drawn. Okay? All right. So that's all that stuff. So then we turn to page 18, bottom of page 18, and there's three little things we need to do, and then I'm going to let you have some work time. So the first one, and remember this was in that course description we talked about earlier, even functions and odd functions. Okay, so let you get caught up here a little bit. Even functions and odd functions. But when we were talking about the prerequisites back here, we were talking about language of functions. And that was, talked about language of functions, domain range, we're going to talk about odd and even, we're going to talk about periodic, we're going to talk about symmetry, we talked about intercepts, zeros, those kind of things. So that's where we're going here. All right, let me give you a couple of quick examples. An even function, here's one right here. Y equals, y equals x squared is an even function. I think you did some of this last year. Does this sound familiar? Y equals cosine is an even function. Now let's look at graphs of those two things. Here's y equals x squared. Okay? Not very good cosine graph. There's y equals cosine. Y, what property do those two have? The ends go the same direction kind of thing. What else? Symmetrical with what? That's called y-axis symmetry, like a mirror image in the y-axis. Y-axis symmetry. Even functions have y. It's like you could fold them on the y-axis and they would fold right on top of each other. Y-axis symmetry. We have a couple different ways we can say that. One way we say that is opposites in, same out. For example, on x squared, I put in a 2, I get out a 4. I put in a negative 2, I also get out a 4. And same thing out. That is y-axis symmetry. Cosine's the same way. Do cosine of pi, I get negative 1. Do cosine of negative pi, I also get negative 1. Same thing. Opposites in, same thing out. And then a more mathematical way of saying that, a more mathematical way of saying that is this. F of negative x is equal to f of x. That is saying that if you put in opposites, x and negative x, you get out equal outputs. F is equal to F. Your outputs are equal if you put in opposites. That's the mathematical way of saying y-axis symmetry. Okay? All right, an odd function. Let me give you a couple of examples. Y equals x cubed. Y equals sine x. Those are odd functions. That's a bad drawing. Should go through the origin. And now you're starting to get used to my drawing abilities. Okay, there's y equals x cubed, there's y equals sine x. These are odd functions. Now yes, the names do come from the fact that x squared is even power and x cubed is odd power. However, just because it's an even power doesn't mean it's an even function. Take x squared, take this parabola and shift it one to the right. Does it have y-axis symmetry anymore? You shift it up and down, it will. But you shift it left to right, and it loses that symmetry. So just because it's got an even power doesn't make it an even function. Okay? And same thing with I. All right, what's the symmetry called here? Not y. It's called, oh, jeez. It's hard to write a y. It's origin symmetry is what that's called. Origin symmetry. Now, what origin symmetry means is if you put opposites in, you get opposites out. Like on the y cube or the x cubed function here. If I put in a 2, I get out an 8. Put in the opposite of 2, negative 2, I get out the opposite of 8. I get out negative 8. Okay? Opposites in, I get opposites out. And the mathematical way of saying opposites in, opposites out is f of negative x equals the opposite of f of x. So you put opposites in, x and negative x, you get opposites, f and negative x. Okay? Opposites in, opposites out. So that's even and odd function. Okay, what will happen on the quiz probably and on your homework as well is I'll give you a function, probably use your calculator because part of the quiz will be calculated. You can graph it on your calculator and you can look at it. Is it even or odd? Now, that's the easiest way to tell if it's even or odd, so you look at a graph because you can see this, you can check for the symmetry and ask you to say why it is. And symmetry would be a good way of saying whether it is or not. Okay, last thing, and then I'm going to let you work. Periodic functions. Periodic functions. Now we all know about sine and cosine. Those are periodic functions. Those are the more famous ones. If you had to define periodic function, if you had to tell your 7th grade brother or sister what made a function a periodic function, what would you say? It repeats, right? I think that would be what everybody would say. It repeats. It's a repeating function. But then we got to be a little more specific. What does that really mean? For example, if I gave you this function here, is that periodic? And the answer is no. No. Because what has to repeat? Or the y value. Yeah, it has to be a horizontal kind of thing. In other words, it has to repeat the same y values over and over and over. And the period is the length at which it repeats them. So sine is like 2 pi. Every 2 pi, you're going to get the same y value over and over and over again. So that is not periodic. But on the sine graph, right here I get a value. 2 pi later, I'll get that same value. That's why it's periodic. Now, here's how the definition is actually written. What this means, whoops, supposed to be an X. So what this means is that you get the same output even if you move over one p value, which is the period, right? Think of it like a shift. If you take the sine graph and shift it 2 pi, it lands right on top of itself. It's the same graph, okay? Now, that's easy to tell if you have a graph. So if you have a graph and I ask you if it's periodic, that's easy. You know, it repeats, it's got the same values, you explain it. But they're going to ask you some other questions that are a little bit interesting. So let me just quiz you on that real quick and then I'll let you work. I give you a function, I'm going to tell you it's periodic. And I'm going to tell you that the period is 2. And I'm going to tell you that f of 3 is 7. That's all I'm going to tell you. What's f of 5? Couldn't fool you. Yes, f of 5 is 7. Because what that means, since the period is 2, that means if you go over 2, you're going to get the same output. Not only if you go over 2, but if you go over any multiple of 2. So if I ask you for f of 11, what is that? 7. Because how far is 11 away from 3? 8, which is 4 periods, right? A multiple of 2. It's 4 periods over. You're going to get the same output over and over again. Okay? So, and then they ask you some variations of that as well. So you can try to handle those. All right, your homework, and I'm going to give you some work the rest of the time to work, is the 1.2 homework questions. Now, I will tell you when you get to 35 through 40, when you get to 35 through 40, you better have some graphs showing on your paper tomorrow when I come around. Um, let me show you this one. 35. Okay, so it's the 1.2 homework questions. Here it is. Whoops, go back. 35 through 40 are using this graph right here, and then they have you stretch and compress and whatever. So I want a new graph drawn for each one of those, okay, based off of this original. So that's some of that stretching, compressing, and that kind of stuff. All right, some of the first questions, they ask you about some points, some x-intercepts, some roots. I would draw little pictures and plot those points and to help you answer those questions. Not that you have to, but I think it could be helpful if you're struggling. Then they give you one, they want you to answer some questions about, you can go ahead and graph it. Okay, if it gives you a function, you don't know what it looks like, you want to look at the graph, you can use your calculator to